it's been suggested that a well-educated person knows about Shakespeare and has read some Shakespeare and maybe seen some Shakespeare plays. That's his picture over here to the right, by the way. A fellow by the name of C.P. Snows suggested that a well-educated person should also know other things other than Shakespeare, and one of the things he suggested that you should know is the second law of thermodynamics and the idea of entropy. So we should go ahead and fix that. So most people have probably heard of entropy before, possibly, but let's go ahead and try and sharpen up the definition a little bit. First of all, the symbol for entropy is given the letter capital S, and it is related to disorder. Or if you like, messiness. But it's just an analogy, and so some people get very upset when I mention the word disorder, but it's a very nice way to think about things. I think the problem is that one person's disorder might be another person's order, so it's kind of hard to decide exactly what disorder means. It's in the eye of the beholder. Alright, so that's entropy, that's the symbol, that's the analogy. What is the second law? So the second law of thermodynamics basically says the entropy of the universe increases. And one way to write that is that any change in entropy has to be greater than or equal to 0. So if you plot a graph of entropy of the universe over time, then this statement basically says it has to keep getting larger. So it can get larger and larger. There can be moments where it doesn't change, but it can't ever go down. So we will never see this happen. Instead, we will see upwards and onwards. So that is the only possibility that we are allowed. Some people have suggested that time itself is entropy's arrow. So what is time? Not real sure, but entropy always increases with time, and so maybe a better measure of time is it simply the direction that increases entropy. Over here on the right, I have a photograph of Boltzmann. Boltzmann was a very famous physicist in the early 20th century, and Boltzmann decided that entropy itself had to be put on a quantitative measure, and he gave us an equation called the Boltzmann equation, and it says the entropy of a system is equal to Boltzmann's constant times by the natural logarithm of W. All right, let's back up here. So this doesn't help us until we know what these two things are. The Boltzmann constant is a very small constant, very small number, 1.38 times 10 to the minus 23 joules per Kelvin. It's essentially the gas constant per individual atom or molecule. So it's just the ideal gas constant divided by Avogadro's number. So it's simply to make it an equation instead of a proportionality. All right, W is more interesting, and W is the number of microstates of a system. And if you don't know what a microstate is, right, that doesn't help you at all. So it's the number of microstates, and that is equal to the number of different ways you can arrange the particles so that they have exactly the same energy. So the idea is that a system that has more entropy just has multiple ways to arrange the system, all with exactly the same energy. We can do a little experiment here. Imagine you've got 4 gas atoms and you've got 2 chambers. And so you've got a chamber on the left and a chamber on the right. And the gas can hang out in either chamber. All right, we can count the number of ways the gas molecules can hang out. So they could all hang out in the left-hand chamber. And that's gas molecule 1, 2, 3, and 4. They could all hang out in, say, the right-hand chamber. So, okay, this looks like a bone or something, right? So 1, 2, 3, 4, okay. Or maybe they could hang out some in one chamber and some in the other. So let's count microstates here. So in the left-hand arrangement here, there is only one arrangement. There's only one way to have those 4 atoms. They're all in the left. And in the right-hand arrangement, there is also only one way to do it. They're all 4 in the right. Okay, now let's go to a difference here. Let's have, say, 1 on the left and 3 on the right. And that gets a little more interesting. So there's 1 on the left and there are 3 on the right. And we can see that there are lots of different ways we could arrange it. So for instance, gas molecule 1 could be on the left and gas molecule 2, 3, and 4 could be on the right. That is a single microstate. All right, gas molecule 2 could be on the left, and gas molecules 1, 3, and 4 could be on the right, and gas molecule 3 could be on the left. That would mean 1, 2, and 4 on the right. And I didn't leave myself enough room. Gas molecule 4 could be on the left, and that would mean molecules 1, 2, and 3 would be on the right. All of these have exactly the same energy. We have not said that there's any difference in energy between one side and the other. So that gives us 4 microstates. All right, we could see that exactly the same thing would happen if we had 1 gas molecule on the left and 3 on the right. Now you might be saying, well, there's another possibility here, isn't there? So if you've got these 2 chambers, you could actually arrange it so that 2 molecules were on the left and 2 were on the right. And if you count up the number of different ways you can do this, it actually is crazy. So you could have 1 and 2 on the left and 3 and 4 on the right. You could have 1 and 3 on the left, so 2 and 4 on the right. You could have 1 and 4 on the left and 2 and 3 on the right. And then you could have 2 and 3, 2 and 4, 3 and 4 with correspondingly 1 and 4, 1 and 3, 1 and 2. So there's actually 6 different ways you can arrange these molecules here. Now, the Boltzmann equation says the entropy is equal to K, so some constant, times the natural log of the number of ways you can arrange the system. So which one of these will have the highest entropy? And the answer is this one right here will have the highest entropy. We know that in general, the second law says that the entropy of the universe has to increase. And so at the end of the day, these molecules will distribute themselves, but we would expect to see this as the most likely distribution here on the right, because this has the highest entropy. If we take S equals K log W, this is going to have the largest entropy of all the systems that we've considered here. In fact, if you imagine starting off with all the gas in one side, and maybe there was a valve here that was closed, it would have a very low entropy, S equals K log 1, which is actually an entropy of 0. And if you opened this up, of course, all the molecules could go to the right side, but there would be no change in entropy. You could have 3 go to the right and 1 stay to the left. The entropy would go up because it would be K natural log 4. But the most likely situation is where you have 2 in each side, and so that gives you an entropy of K natural log 6. So gases tend to expand to fill out the available volume, and in doing so, they have an increased number of microstates, and so by the second law, that leads to an increase in total energy. Another way to think of it is God plays dice, and so it's all a dice game. The most likely thing is the most randomly occurring, the most frequently occurring event. So if you roll 2 dice, I mean, you might see, a 1 and a 1 or a 6 and a 6, but the most likely combination is that the 2 numbers add up to 7. So we're basically just gambling in chemistry.